Okay, hello everyone, my name is Attila Barsi. I come from the company Holografika, and I would like to talk a little bit about GPU-assisted light field capturing processing. Or do I? What I really want to talk about is ninjas, because we have this motivation that ninjas are really cool, and we would like to do lots of tricks that they can. The first trick that I like very much is illusions. So what do we want to do? We would like to visualize all kinds of 3D scenes in thin air, especially ones that we've captured as live scenes, so not only virtual scenes, but live scenes as well. In order to do this, unfortunately, because we don't have Chakra and magic, we need physics and mathematics. So I would like to introduce you the light field concept, which is a measurement concept. We would like to measure a vector field. We would like to see how much light goes through in every direction through every point in space. Okay, we can already see that this is too much data. So clever physicists will already know that we would like to reduce the amount of data that we want to handle. So how can we describe this? We can describe this with a 5D panoptic function, which describes the ray with x, y, z, and two angles. and the result is the luminance of the light that goes through that point to that direction. Okay, so how do we want to reconstruct this panoptic function? We would like to impose various restrictions like discretization of this function, and instead of radiance, we would really like to use RGB because all of our equipment captures or reconstructs RGB. In this sense, we can generate a light field display. If we manage to have some kind of light emitter that we can control, and if we can collect them in a single device, then we can call this a light field display. We can at least control the intensity of a few points in space to various directions. We can include various properties of light. We can incorporate various properties of light into our device. We can incorporate light origin, the various directions that we want to change. We can incorporate the light color, so we can have color displays, the intensity, the polarity, and the phase. Usually, the human eye doesn't really care about polarity and phase, so we can probably skip that, but there are some more complex systems that also would like to reconstruct this. This generic sense of light field includes pretty much everything that you can imagine, from a single LED light source through 2D displays, stereoscopy, photostereoscopy, and of course the holy grail, full parallax holographic systems. We would like to restrict this a bit because, unfortunately, this is unfeasible to build a full light field displays. As I've already told you, we would like to discretize this and get rid of everything that the human eye can't see because we are not building stuff for robots yet. What would we like to do? We would like to emit controlled light in every possible direction through every point in space. The closer we can go to this, the closer we are to real light field display. We have two special cases that we can build that are close to this restrictive sense of a light field display. One of them is the horizontal parallax only autostereoscopic display that controls the light color through every direction in the horizontal. And in the vertical, it will diffuse the color. So in the vertical, you will see the same, and in the horizontal, you will see different colors as you move in front of the display. And other special cases, as I mentioned, is the holy grail to build a full parallax autostereoscopic display. Let's see what we can accomplish today out of these goals. What we have is a HoloVizio system, which is composed of optical modules and a holographic screen. As you can see, colored light beams come out of the optical modules. They act like projectors. And these colored light rays hit the holographic screen at various angles of incidence, and the exit angle will depend on the relative position of the screen point and the relevant modules. We know that in order to generate differently colored light beams in different angles, we will need some kind of direction selective property of the screen. And because we are horizontal parallax only, we would like to diffuse the color in the vertical. The emission angle is going to be geometry dependent, so that we can avoid all kinds of optical roadblocks that make our life really hard, like Fresnel lenses or anticolor lenses or parallax barriers. Because these will introduce all kinds of visual artifacts and other things in the system that we would like to really avoid. Okay, I would like to introduce the field of view as a concept. So the field of view is the viewing angle where you have a valid image in front of the display, but inside the field of view you have a valid image everywhere. So like as opposed to other styles of autostereoscopic displays where you have sweet spots, in the HoloVizio system you have a continuous motion parallax that you can move in. And I would also like to introduce the angle resolution for the sake of this talk. So, as I've already shown you, quite a large number of light beams can be emitted from the same pixel area. And this angular resolution will determine the field of depth. So the more light beams I can get through the same angle, the higher angular resolution I have, and the more light beams I can let through, or I make in the back, the more depth I can visualize. Because the denser the light rays are, the more precision I have farther away from the screen. And we know that the density of the light rays will decrease when I move out of the screen. So I have this achievable resolution that will decrease from with the distance from the screen. What's special about all kind of rendering and conversion from real-life cameras, like pinhole cameras, to the holographic screen or to the HoloVizio system is that we have a light field reconstruction. As you can see, we have a bunch of rays going all over the place, and one viewer position will see rays from multiple optical modules. So a module is not associated to a viewing direction, and the projected model image is not going to be a 2D view of the final 3D image. Each view comes from more modules, and we designed the system so that the number of contributing modules doesn't change over the FOV, so you see the same high resolution image wherever you're standing. Okay, as I already told you, we have continuous motion parallax. Wherever you go in front of the display, inside the FOV, you should be able to see a nice 3D view. Okay, I would like to introduce a couple of our systems. I will go over this very quickly. So we have the 722 RC, which is a 72-inch display, which features a cluster. And now we come to the original topic of this conference. So the cluster, incidentally, has a couple of GPUs, which we are going to put to work very soon in the talk. And it has LED-based colors, so it has a nice uniform image and also a very bright. Okay, we have a full-angle HoloVizio monitor, which you can walk around in a half circle. It is a very, very high resolution, very high degrees field of view. It also features LED colors and it has multiple DVI inputs. If someone has experience with GPUs, then you can already guess that only a few GPUs are necessary to drive this display. Actually, we are only using 2 PCs as a cluster to drive these types of HoloVizio displays because we have monster NVIDIA graphics cards which have 4 display connectors coming out from each of them. So overall, I think there are 20 TDI inputs which we drive from a 2PC cluster, which is, I think, pretty cool. Okay, and the last one that I would like to show you is going to be a cinema system, which is quite big. It's a 140-inch diameter display. Again, you don't need any kind of glasses or any kind of, there are no optical contradictions like you have with huge stereoscopic systems. Also features LED-based color, and it's very, very bright. It's really bright, so like this is very bright. It's, I think, brighter than the cinema that you can go to. I mean, the regular cinema, regular 2D or stereoscopic cinema. Okay, this is for light scale simulation and for cinematography. And this is the last one that I would like to introduce. This is a special display that we are experimenting with. Like this is the closest to the original Ninja image that I've shown you. So pretty much you can, as you can see, you can do this with the screen. So it's pretty much screenless. You can touch the objects inside because there is an ultrasound imager, like an ultrasound projector, this small stuff here, which can generate you a gentle buzz on your hand whenever you're touching virtual objects. There are also simulated light and shadow, where you can see the shadow from the virtual world can hit the real world. Again, it's physics instead of magic, but it's really cool. And of course the real light, so I don't know if it's visible, but this is a oops. Okay. So this is a stand lamp, and the stand lamp is registered into the virtual world, so you have a light source in the virtual world coming from the stand lamp. Okay, anyway. What are the benefits of using such light field displays? You can view it with the naked eye, so you don't need any kind of additional equipment. So ninjas have forehead protectors, so don't do this with your forehead protector because your eyes will look like this. No glasses, no tethers, no tracking, no positioning, no image jumps, which is really cool. It also features a wide FOV, I think the widest in the industry. And the virtual object position can be anywhere. It can be behind the screen, in front of the screen, on the screen. This is also a feature that is not common with autostereoscopic displays. Usually they are like a water tank where you can only see what is behind the screen. Okay, it enables multi-user collaboration because if I point at a point in the virtual space, then everybody will see the same point. This is not really true for stereoscopic systems, where the tracking is tied to one person, and he sees something in the virtual world and tries to point at it, and everyone else will see a different point, depending on their viewing position. You can imagine that the 3D movie becomes something else, so it's not going to be tied to a certain position anymore, so it's going to be much more closer to a theatrical performance, which was the original idea for a TV anyway. Okay, let's get back to track. So we would like to capture some kind of real-world images for this kind of setup. In order to do this, you can imagine that we need to somehow measure the light in various directions of the scene. We will need a bunch of light sensors to do this. What is available today? What kind of light sensors are available today? Everyone has a digital camera probably in their phone or at home. So we have these kind of pinhole cameras, so we can simplify the current cameras as pinhole cameras, Or we can use panoptic cameras that capture through a flight's eye lens much more of the light rays that are present in front of them, or much more of the sea, of the light field that is present in front of them. We can build two types of camera systems. We can build camera systems with dense sampling, so like where the light sensors are removed farther away from each other, or we can have dense sampling is where you have one or something very close to each other, but with a high resolution and with some optics that will take the light field with a very dense sampling in a small FOV. Or you can have a sparse sampling which takes a light field in a wide FOV, but much sparser, with much sparser sampling. We need to check the design and the characteristics of our display in order to have the correct camera system. Because if we screw up the camera system, then the display will not be able to visualize correctly the light field that we wanted to capture. If we don't manage to capture enough angle or enough light ray density, then we will have sampling errors on the display. Okay, what can we do if we have this kind of capture equipment? We can do ninja hiding. We can hide or remove all types of image errors. We can change the focus and aperture, and we can hide occluders from our light field. So this is like one application for dense light field capture, where you have a camera like this, which captures on a small baseline, so there's a small difference between the two farthest points of the camera captures eye positions. We have a micro-lensing optics in front of a normal camera, a high-resolution normal camera, which will result in a high number of 2D images. And this type of arrangement usually supports both vertical and horizontal capture. This is what it looks like. So there is a fly eye lens, and through the lens you capture multiple directions and multiple angles of the same scene. With this, you can do light field refocusing, which is a very nice, which is a technique, which is an algorithm that can be very nicely fit on the GPU. You have these images that focus on different planes in the scene, and you can simply average the captured rays based on the camera that you want to simulate. So if you want to simulate a camera that has a focus on a certain plane, then you just need to sample the rays that went into your light field camera, so that you only apply the rays that match the focus point of that specific camera. So like these nice depths of field effects can happen if you do this. Like you can change the focal length of the camera after the shot, which is really cool. So as you can see, they either do this by using the mathematical model of the lens, or they have some kind of measured or ray traced model of the resulting camera, and this can be pre-computed and just load it up to the GPU, and then we just read the necessary rays from the ray table, from the color table of the captured image. And the result is going to be a nice refocused image, or a nice image where we change the aperture of the camera. Okay, and we can also hide stuff. So this is called light field completion, where we estimate depths. From the images, we can estimate the depths of the various objects that are on the scene. We can generate a selection mask like this one, and boom, there goes it. So like we can remove occluders such as fences, raindrops from the camera image, and so on and so forth. because we have other light rays that go to the same point, but are not going through the occluder or the smudge or the raindrop that we have on the camera. This fits also very nicely the GPU computation, because in the simplest case, you just have to generate a median image from the light field to find the object behind the occluder. Of course, there are more advanced techniques. There are some references after the talk. So if you're interested in this, then you can dive further into this kind of light field technique. Okay, what we are much more interested in, which is much closer to our light field displays, is the sparse light field capture, where you have a huge number of cameras mounted to some kind of rack, like the Stanford camera or the Fraunhofer IS light field camera. So again, this can be horizontal parallax only camera system, where you only have the cameras on some kind of arc or line, or it can be full parallax, so horizontal and vertical parallax system like these two. Density, of course, will depend on the camera size, because physically you have to place your small pinhole cameras next to each other. And you can make nice captures like this of 3D scenes, and you can do all kinds of cool stuff that we already mentioned with these cameras. Okay, now we have a capture of the real world, some kind of light field capture, where we capture multiple directions from a camera arrangement, and we need to display this on our light field display. So we need to resample the capture light field to the display light field. This is a task that is ideally suited again for the GPU, because we have multiple tasks that we can all parallelize. One such task is to ray trace the display's light rays through the display's optics, the mathematical model of the display's optics. And once we get the ray table that represents the outgoing rays from the holographic screen to the eye positions, then we can use this to find the necessary rays from the captured rays, from the camera rays that we have. How do we do this? We take the display ray, we find a bunch of cameras that are close to this ray, and then we project the starting point of the ray, which is on the holographic screen, into the cameras. And by projecting this point, we find the point on the camera and on the camera image that we want to sample. So this is going to be our sample point. Okay, and then we just have some kind of measurement, like angular difference or something like that, or tangential difference between the camera ray and the display ray, and then we interpolate based on how well the display ray matches the camera ray. Just to show you some code as well. We have everything in GLSL, so everything pretty much is either in OpenCL or GLSL compute. This is actually a fragment shader, a GLSL fragment shader, which tries to do light field conversion. So we have two cameras. Each of them have camera index, camera XY coordinate, and weight. I mean, the first one has weight, the other table doesn't have the weight, because you only need one way to interpolate between the two sampled colors. So we take these values, and then we just make a simple lookup out of the sampler to the array of camera images. With the first one, the second one, and then we do the interpolation, which is a mix. And this is going to be our final display color. So everything is pre-computed, and then we can do on-the-fly rendering
Okay, let's talk just a few words about color spaces. So what kind of color spaces do we have on cameras? We have via RGB. This is what is actually captured in the camera. There is a filter mask in front of the sensor, which filters for red, green, and blue. And this is 8 bits per. This raw image is 8 bits per pixel. And this is what the camera sees. This is what you would like to use for RGB conversion. If we have a camera, usually for industrial gigabit Ethernet cameras, this is supported that we retrieve the raw image. Some cameras feature luma and chroma in planar memory arrangement, which can be either 12 or 16 bits per pixel. This is also very easy to convert into RGB. There is a 4x4 matrix that can convert to RGB. And of course, you can also retrieve RGB, which is 24 bits per pixel. So we try to avoid this because this generates CPU load. It's not really nice. So we can also do GPU wire demosaicing, which I will not talk too much about. So instead of letting the driver do wire to RGB conversion on the CPU, we port it wire demosaicing into the GPU, and we will do it only when necessary. We also need Ninja equipment. We need lots of hardware to do capture. We have this kind of big camera setup, which we sell as a camera array, which features 48 modified IPS cameras with high resolution, and we have 4 times 10 gigabit Ethernet access to this camera setup. How does it look like? We have these IPS cameras, we have a power over switch, we have a huge PC, which you can see here are the 10 gigabit Ethernet uplinks, and here are the 40 gigabit Ethernet downlinks to the render cluster. So it features a really huge bandwidth. Okay, why is this important? Because we have a camera broadcaster software, which is massively parallel. As you can imagine, we handle all the cameras in parallel. We have a few additional threads for synchronization, and then we cut all the data, all the data that are necessary for a single renderer to work, and transmit them over the 40 gigabit Ethernet to our render cluster, and then we render the images. This is the cut shader. So this is again GLSR compute. So we just search the table, and we just do atomic min and atomic max on the camera coordinates, and we store the bounding box of the necessary regions per camera. We send this to the broadcaster so it knows what to cut. Okay, what is our last Ninja motivation? We would like to replace real cameras with virtual ones because real cameras are very expensive and hard to mount, and we want to increase the density of our system so that we have a better image. Okay, we would like to do sparse and slide field generation. For high angular resolution displays, the 48 cameras are not enough. So we would like to estimate some kind of disparity or depths from our camera images to interpolate more cameras into our camera system. How can we do this? We can do disparity estimation, which is a classic image processing method, which is very well suited again for GPUs. What it does is it searches on rectified images along a horizontal line, and it tries to find corresponding pixels. So for each left pixel, it will try to find the right pixel that matches the same point in space. And from the camera parameters and the disparity value, we can determine the estimated depths. There are many algorithms for disparity estimation, and once the disparity estimation is done, we can do the interpolation, and we can do the light field conversion on the estimated images. Okay. What happened? Okay. We can estimate both left to right and right to left disparity, and we can increase the precision. We can do rectification, which is again an easily portable test for the GPU. This is a rectification shader that takes into account a couple of distortion parameters and the intrinsic matrix of the camera to generate the rectified images so that we have perfect horizontal alignment for the two images. Okay, we can do image interpolation, and this will result in a couple of errors, which we can again fix on the GPU with some nice image processing algorithms like inpainting. We've also evaluated these type of algorithms, and we found that for very, very sparse camera arrays, it's much better to do depth reconstruction, which is much more costly, but the end result is much nicer. So we have this multi-view depth estimation pipe, where we do segmentation and we do an initial depth estimation. We refine these depths from the neighborhood, and then we do depth map fusion. So we take the various depth maps from the multi-view image array, and then we try to correct the errors that are still present in the depth map for the current camera. Okay, super pixel segmentation has been implemented on GSR compute. We ported it from a CUDA implementation with our own modifications. It's a multiplex GPU algorithm. The depth estimation uses depth sweep to find correspondence between the various segments in the images. We do depth map refinement with energy minimization, where we take into account the smoothness term and the consistency term to find the correct depth map values. And finally, the best part in this is that once we have depth values for all images, then we don't need to do the interpolation. We don't need to find the virtual camera positions. We can simply render based only on the depth maps and the color maps directly into optical module images, because now we are on, this is the last one. Okay, so to conclude, light field capture is very hard, needs lots of equipment, much more software. We try to reduce the bandwidth as much as possible, and if we have the correct depth estimation, then we can render directly into the light field image, so we can avoid this very costly image interpolation error correction. Okay, that's it. I would like to thank my contributors for their work, and I would like to say that lots and lots of EU projects have been putting much effort into generating code, generating GPU code for this kind of pipelines. Okay, there are a few references here to what I was talking about, and thank you everyone for your attention.
Okay, thank you very much. So since you have the presentation table and we are lack of time, so if you have one or two burning questions, please come with us.
Yes.
Just want to understand, so it's 30 million pixels, am I right? Does it mean actually 30 million pixels times directions in one of the systems, or it's
it's overall
times 35 dimensions?
No, it's like it was 80 million pixels and overall. So it
includes the directions.
Yes,
but roughly, is it a trade secret? Like, how many directions are there per location?
It's very hard to say because of the optical arrangement. How many directions are? It's viewpoint dependent. So if you stand on one viewpoint, I will be able to ray trace you how many light rays are going into your eye. Otherwise, it's very hard to tell. But it's around 180 to 200.
It's over 100. Okay.
It depends on where you stand. So if you really are in the back, then it's less. If you are very close, then it's much more.
Thanks.
You're welcome.
One more question. Okay.
Yes,
No, so Attila and the whole set of the devices during the coffee break, you can try the devices and you can ask more questions. Thank you very much again.
Thank you.